Welcome to Study Loop.
In this question, we are calculating the elastic potential energy, gravitational potential energy, kinetic energy, and total energy for an object that is oscillating vertically on a spring. So we are going to, for simplicity, depict this scenario as a box, and I'm not going to, we'll draw it as a spring. So we are told, actually I need to draw that a lot bigger. So we are told that the highest position of the oscillation, that's not nearly enough coils, the highest position of this oscillation for this box is the unstretched length of the spring. And that's, that box was supposed to be. It doesn't matter if we measure the box or the spring, because that little bit is constant for all of it. So this is now, we're going to call it x equals 0, right? Because this is where we have no stretch. And then, just for convenience, I'm going to label the bottom of our stretch. We're going to pretend this thing could go all the way down to the bottom of my table here. And so this is going to be where we have a height equal to 0. We are told that there is an amplitude of oscillation equal to 0.05 meters. So this middle dashed line that I just drew is the equilibrium position, which I've labeled EQ. And so our object, our cat, is oscillating with amplitude A around that position. And so this lets us begin to see that at x equals 0, the unstretched length of the spring, our object is elevated a height of 2a above its lowest possible point. And then we also are going to know that at the highest point and the lowest point, our kinetic energy is going to be 0. And we're starting to now form a picture of how to approach this question once we have this diagram to help us visualize everything that's going on. So at the highest point, so we know that elastic potential energy is calculated with 1/2 kx squared. But since x is 0, we know that this is going to be 0 joules. And similarly, we know that when our cat is at the highest point of its bounce, the kinetic energy, which is 1/2 mv squared, is going to be 0 joules again, because v is 0 at the top. And I'm going to go ahead and go back and add over here because x is 0 meters. And so this tells us then that all of the energy stored in this system is going to be from the gravitational potential energy. And we can calculate gravitational potential energy with mgh. And like we discussed when making our diagram, that means we need mg times twice that amplitude. So we'll take our 4.0 kilograms times 9.8 times 2 times 0.05 meters for that amplitude, and that gives me a gravitational potential energy of 3.92 joules. Oops, that 9's a little bit close to my decimal point. There we go. And now it looks like a 7. Let's try this again. There we go, 3.92 joules. And so our total over here is going to be 0 plus 3.92 plus 0, which is going to be 3.92 joules. And now, because this is a conservation of energy problem, hey, that means our total energy in this system is going to be 3.92 joules for all 3 positions. This is because of COE, conservation of energy. Okay, so now let's take a look at that lowest point. Once again, we now know that our kinetic energy is 0 joules for the same reason as before, that the cat's not moving. And now we're going to know that our gravitational potential energy is 0 joules. Again, because our cat that's bungeeing on this thing is at the lowest position. The height is 0 meters. So that means now that all of our energy must be elastic potential energy. 3.92 joules. Woo! And I'm actually going to move that up. Well, no, we'll leave it. We'll leave it as is. Because I was going to point out that we could use this then to figure out the spring constant. But I'll leave that for when we go to talk about the equilibrium position coming up. So, yeah, at equilibrium, we are going to have some stretch of the spring, some elevation of our object, and some kinetic energy. Oh boy, where do we start? How about we start with the fact that, let's grab green because green will be fun. How about we start with the fact that we know that the cat's elevation at this point is just going to be equal to A, the amplitude, when we go to this equilibrium position. So we can say 4 times 9.8 times 0.05. You know, we're going to just put that on the next line after all, just because I want you to be able to read it. And so, not surprisingly, this is half of the maximum, which gives me, because we're at half the total elevation, right? 1.96 joules. Sorry, I was turning the page in my notebook. 1.96 joules. And so then the question becomes, well, how do we divvy up the remaining 1.96 joules? And so we have 2 ways that we could approach this. The next thing we're going to be able to figure out is the elastic potential energy. And then kinetic energy is just going to be whatever is left over. I'll give you that spoiler alert. To find US at equilibrium, one way will be to use proportional reasoning, and then the second way is going to be a straight-up calculation. I will show you both ways so you can decide which makes the most sense to you. So for proportional reasoning, we can look at the fact that US at the top, I'm going to call it UST, is US at the bottom. I should be a little bit, there we go, better with that, that's when we had 1/2 K times 2A squared, which we could say is 4 times the quantity 1/2 Ka squared. And that is going to be equal to 3.92 joules, which we established in the previous step. Right, but now our elastic potential energy at equilibrium, our spring is only stretched a distance A, so 1/2 Ka squared. So what we're really saying is that at our maximum stretch, we have 4, actually let me write that a little bit differently. So at our maximum stretch, we have 4 times the equilibrium amount of elastic potential energy because we don't have a linear relationship here, right? We have a quadratic relationship between stretch and energy. So when we double the amount of stretch, we have 4 times the energy. Or if we're comparing to the bigger energy, when we have only half the stretch, we're going to have 1/4 of the energy. So we can now say that the elastic potential energy at equilibrium is going to be 3.92 times 1/4, which gives me 0.98 joules. And now if I wanted to do a straight out calculation, what I would do is look at the fact that US at the bottom is 1/2 K times 2A squared, and we know that it equals 3.92 joules. And so I would go ahead then and substitute. 1/2 K times 0.10 squared equals 3.92 joules, and I will solve for my spring constant, which is going to be 2 times 3.92 divided by 0.10 squared, which gives me a value of K of 784 newtons per meter. And now I could calculate elastic potential energy at equilibrium with 1/2 times 784 times a spring stretch of only 0.05 meters, and I get 0.98 joules. So whichever way makes the most sense to you, you can do. I personally like the proportional reasoning, but that's just me. And now our kinetic energy is going to be whatever's left over, right? So we'll take our 3.92 minus 1.96 minus 0.98, and our kinetic energy here at the end is going to be that remaining 0.98 joules.